JJ? Not yet, but.
Hello, everyone. We're just going to give it a minute or two to let people trickle in, and then we'll get going.
Are you busy there?
Awesome. Already, we can start it off today. So hello and welcome everyone to our webinar today. I'm Nicole Rathie, the project manager for AI for Manufacturing Canada. Today, we'll be speaking with industry experts on the difference between AI in manufacturing and automation. We'll be joined by Robert Ziner, the founder and CEO of Advanced Biomaterial Technologies Corporation, a company that is transforming agricultural waste into high-performance plastics. NIRAV RAIYANI is a research engineer at NTWIST, a company that helps industrial sector leverage their data through AI. We will have a question and answer period at the end of our session today. Feel free to drop your questions in the Q&A box or raise your hand during the question and answer section, and we can unmute you if you'd like to ask your question verbally. Without further delay, I will pass it off to Robert to start us off today.
Thank you, Nicole. Give me 2 seconds and I'm going to set up my screen. That's not presentation view. Okay.
Awesome, Robert. We can see your screen there.
Excellent. Can you hear me?
Yes.
Very good. So, good morning. Thank you all for joining NIRAV, Nicole, and me to discuss the difference between automation and AI in manufacturing, which I will now refer to as AI for M. My name is Bobby Ziner. I sit on the board of NGen's AI in Manufacturing Association, and I'm the founder and CEO of Advanced Biomaterial Technologies, which has developed and patented an AI-driven smart factory for processing hemp stock into fiber. I have been involved with advanced manufacturing technologies focused on optimization since 1989, when I partnered with GE's Factory Automation Group to design, patent, and build a computer-integrated manufacturing application to redefine the economics of large-scale secondary wood processing. We built our new factory in 1997, which helped my company increase our revenue from 37 million in sales in 1997 to over 240 million by 2001, only 4 years later. Our proprietary OptiStress system enabled us to become a well-recognized, large-volume, high-quality, low-cost provider of custom wood products. When I started preparing for this presentation, I spent some time thinking about how I could best describe in one word the essence of AI in manufacturing. Business intelligence ensures that a company has access to all the relevant information which it needs to know to serve its market as well as possible. It identifies all the elements of a company's operations which need to be working cohesively for it to operate at its best. To be truly effective, all of a company's operations need to work together. They all need to be optimized into a unified structure. In my opinion, it is business intelligence that defines the need for AI for M, and a successful AI for M solution provides immediate, direct access to all of a company's business intelligence. Let's start with the question, how relevant is AI in manufacturing today? Well, I think a 47.9% CAGR projected to 2027 pretty well tells the whole story. 709% growth in 5 years. AI for M is clearly where global manufacturing is heading today. Now, let me show you why. Manufacturing operates in a very competitive business environment. Its basic focus is how to produce more products for less money. Please follow this chart with me, starting at the bottom left of the screen. The first 4 steps, right up to 1984, were built on finding new production solutions to generate more saleable output. Automation technology innovation was strictly focused on maximization, the ability to produce more. Then, in the early 1980s, computer-integrated manufacturing was introduced. This was essentially today's IoT, but without the internet, the entire network being limited to a company's own computer system. The opportunity was to integrate multiple computer systems and digitally driven machines within an AI-controlled system architecture and a very powerful database to control an entire manufacturing facility in real time. The plan wasn't to only output more product, but to generate better product, more dependably and more cost effectively. The principles of optimization had finally entered the world of manufacturing. Finally, about 15 years ago, AI for M emerged, offering more data access via the internet, better operating controls, digital twins, faster and more flexible processing, along with easier and more potent optimization capabilities. In an automation environment, the focus has always been to maximize the output. As a prescriptive solution, automation relies on following inflexible, rigid, preset rules and instructions to simplify the production process and increase throughput. In AI for M, the aim is to have a solution which addresses all the needs of the business in the most practical and profitable way possible. As a predictive solution, AI for M relies on analyzing real-time as well as historical data to achieve the most profitable solution. What data is important to consider in manufacturing? The most appropriate answer would be the pieces of data an expert in the field would ask to see. That is why AI was originally called expert systems in the 1980s. In all manufacturing environments, improving productivity is a central consideration. However, in most manufacturing applications, there are at least 9 data considerations which need to be analyzed in order to optimize the result. The key to continuous improvement as a company is its business intelligence, and being able to identify and control its critical factors. That is the end goal of optimization. And it is something that people can simply not achieve in real time, regardless of how many people are involved. The power of AI for M is its real-time processing capabilities, which enable a computer to optimize a manufacturing operation by being able to monitor, track, control, coordinate, and synchronize multiple layers of data and data communications. With automation, there is only one layer of data being monitored in real time: throughput. So let's take a quick look at how the ability to process multiple data streams leads to optimization. One, you need the facts to get the answers you need. Two, you get access to these facts at the same time. Three, you fulfill as many of your needs as possible. The best alternative is the one which optimization predicts will fulfill as many of the individual needs as possible. AI-driven optimization is the only way to predict the best solution to multiple needs. And it is the only tool that can get you there. And that is because it's a predictive process. The total operations of a manufacturing company go well beyond just making things. And while many of these operations may seem to be incidental, they are all, in fact, critical to a business to ensure ongoing profitability and long-term customer satisfaction. These operations include data analysis, human resources, production planning and forecasting, equipment maintenance, production and distribution, just to name a few. But everything needs to be considered in real time. Intelligent optimized manufacturing already exists and is very much proven. Industry 4.0 introduces the real-time digital integration of all the manufacturing technology, engineering, and machinery in a facility, thus making them all programmable, even from remote distances. Various sensors and scanners identify and track specific data in the manufacturing process and feedback this data to the system using real-time digital communication technologies, thereby allowing the data to be automatically recorded, filed, and analyzed. The data then gets digitally communicated and automatically engages digitally driven equipment to execute the next step without relying on any human intervention. By being able to optimize every independent need of a specific manufacturing company, its bottom line is optimized. And it is also important to note that this level of immediate access to data will have a substantial impact on the company's entire supply chain. Why? Because in the manufacturing world, transparency counts. Digital twins are a 100% virtual replication, including all engineering restrictions of all the equipment in a production line and all its associated software systems. A digital twin also enables real-time software tweaking. These benefits completely eliminate the need to build prototypes or a pilot plant, both physical and software. The cost and time savings from this alone are huge, unbelievable. Machine learning optimizes everything, not just the production process, including materials, productivity, labor management, and energy. It also enables automated continuous improvement in operations, which helps to redefine the economics of the business. And very significantly, it reduces energy consumption and equipment maintenance costs by monitoring every pump, every drive, every valve, and every motor during all processing. A digital twin relies on AI-driven software to virtualize the design and engineering of a digitally driven piece of equipment or production line, so that it can be used to do real-time simulations of manufacturing during the process, with all the decisions and actions being directed by digital instructions without any human intervention. For example, when defining the engineering needs, a programmer can immediately visualize the impact of a bigger or smaller pump or motor in real time on a computer screen by simply clicking on an icon, just as you would when selecting your preferred race car in a car racing video game. Digital twins accelerate predictability by being able to optimize virtual data in real time. In summary, these four categories: improved asset efficiency, improved product quality, reduced costs, improved safety and sustainability, and all of their subsets shown in front of you on the screen show the actual operating results a manufacturing expert focuses on. And you can see from Deloitte Consulting's 2023 presentation just how effective they are. These are the areas of business intelligence every business operator needs to consistently improve. Look at the disruptive improvements which are generated by optimizing business intelligence, including improved safety and sustainability. Add these improvements all together, and it's easy to see how AI for M redefines the economics of most processing and production applications, and how business intelligence defines the need for AI for M. AI for M is the manufacturing world solution to business intelligence. It collects it, analyzes it, and makes optimized decisions. That is intelligence. And that's the critical difference between automation and AI for M. Thank you.
Thank you, Bobby. That was great. I will now pass it on to NIRAV, and he can share his screen for us.
Thank you, Nicole. Thank you, Robert. Okay, just share my screen. Can I see my presentation view?
Yes, we can.
Okay, oops. Just a minute. Thank. Can you see my screen?
Yes.
Okay, sorry about that. So, hello everyone. Thank you, Robert, for giving us a good 360 view on AI in manufacturing. So what I would like to do is I would continue this presentation by discussing a few steps in more details. And yep. So when we think about AI in manufacturing, I think it's usually about bringing the operations towards autonomy. And I think so between automation and autonomy, I think they follow this three simple steps. So when you have automation, what happens is usually you send something, then you analyze it, and then you act on it. On the other hand, when you have autonomy or AI involved, there's this added layer of intelligence. So now your sensing becomes perceiving, your analysis becomes understanding, and your act becomes solving. I would like to use a simple example to understand to explain what I mean by that. So let's take a look at this this square. So in this, there's a car that is coming with certain traffic conditions where your traffic line is green, your speed limit is 70, and there's a person who is planning on crossing this road. Now let's take a look at how these two technologies, automation and autonomy would react to the same situation. So on one hand, you have cruise control, which is a good example of automation. So the way the cruise control would handle the situation is it is asked to go at the speed of 90. So it would first sense what is the present speed, which is 60 right now. Then it would analyze it, and then it would realize that it is 30 away from where it should have been. It wouldn't care what is the present speed limit, which is 70. So it would know that it is at a lower speed than it is instructed to go at. So it would increase basically the speed by pushing the gas pedal. On the other hand, you have FSD, which is pretty hot right now, which is fully self-drive. So here there is this added level of intelligence. So when it senses, it would basically collect all the information that is available in a meaningful way. So first it would collect that the traffic sign is green, the speed limit is 70, and there is a pedestrian that was detected. Then it would understand that if the traffic sign is green, so it is good to go. The speed limit is 70. Right now it is at 60, so there's no problem there. However, there's a pedestrian, so there might be a collision. And based on that, it would try to solve this problem by either applying the brakes or changing the directions, or probably by doing the both. So basically, these are, I wouldn't say these two technologies are different. It's just this added layer of intelligence that makes them different. And the way I look at it is like this, that on the one hand, you have humans, and on the other hand, you have machine, and the number of tasks that are carried by either of this would basically define what is the level of autonomy that you have. So in the case of car, if you're completely driving it manually, then you have it's completely driven by humans, so there's no machine involvement. Now you add cruise control to it, so now you are relying more on machine to basically handle your speeds. Then you add adaptive cruise control, so the human is still in charge, but now even the brakes are handled by machine. Then you add lane assist to it, so now you're giving your control of steering to the machines. And then at the end you have FSD, which is what we just have seen. So up till this point, human was in charge. However, we are moving towards autonomy as we go down, and at the end you have autonomous vehicle where human does not have a control and it's completely handled by machine. So this is how I look at AI. So this was a simple example of a car, but what I would like to do now is use an example of an industrial setting to see how these things are different in industry. So let's take an example of a pump station that is operating using automation. So the goal of the pump station is to transfer certain amount of oil from point A to point B. And the way it does is by using the pump to push this oil down the line. And what usually happens is this line is so long and you have peaks and valleys. So it may just one pump may not be able to push the oil all the way through, and you would have some intermediate booster stations, which would again have some pumps. And when you have automation, the way this entire system is operated is like this, that you have a control room where an operator would be sitting, and it would order this control loops that you would have at each of these pump stations. And it would order this control loops to maintain certain pressures at each of these pump stations. And this controller then would just take this pressures and then it would just maintain it. So how that would work is again the same, sense, analyze, and act. So say, for example, an operator is asking a controller to maintain the pressure of 1500 kilopascal at a certain point. So your set point becomes 1500. So you have a pressure gauge, so you would sense what is your present pressure, which is somewhere here. then a controller would analyze whether it is up or down, and based on that, it would ask pump to basically run faster or slower until it reaches its 1500, and then it would maintain it. However, the interesting part is that when you have this kind of setting where you have lots of pumps, your goal is to achieve some flow rate so you can meet the demand at the receiving end. You can achieve the same flow rate by using multiple settings. So there are multiple ways to achieve the same flow rate. For example, you could probably use just one pump at the first station, then you can use two pumps at the second station and just one pump at the third station. And you would still, you would be able to maintain the flow rate of X, say for this is for the example. Now, the another way of achieving the same flow rate would be just using the two pumps instead of one at the first station and then one pump at the second station, and it's doing the same job. However, when you look at the energy consumption, and the first configuration is costing you more, while the second configuration is consuming less power. But on the other hand, the power consumption is not the only thing that you look at, because when you are operating this pipeline, you also have to keep in mind the pressures that you are ending up with when you are making certain selections, because high pressures or fluctuations in pressures, it could damage your pipeline, it could result in leaks, it could basically burst your pipeline. So there are lots of things, and it could ultimately reduce the life of your pipeline, which again comes to the capital cost. So there are lots of things. So this is the and the way it works with just the automation is that a control room operator, based on their own experience, they would make these selections and operate the line. Now let's see how, when we move towards autonomy, this situation would change. So throughout the line, you have lots of sensors installed. So when you have an autonomy, you first take readings from all these sensors and you perceive. So basically, what happens is using the sensors, at the same time, you would be able to know how are the pressures at each pump stations, what is the kind of what are the properties of the fluid that is at each pump, so what is the density, what is the temperature, what is the viscosity, and everything. So first you would perceive, then it would go to this optimization engine, which would try to understand. So what it understands is that this is the present condition of my line, and it would also know your business goals. That means the flow rate or the flow that you want to achieve, along with other things like business goals and everything. Then it would try thousands of permutations and combinations, and it would run it through this machine learning models, which would basically tell optimization how a line would respond to each of these options. And what optimization engine would then do is, for each of these options, it would try to see and assess the business goals. That means it could be a power consumption, it could be achieving the flow rate, it could be the physical limits of the pipeline, the safety, or as I said, like the good operation limits, which basically improves the life of the pipeline. So those things, and based on these business goals, it would assess each of these options, and then it would come up with the best setting or best recommendation that fulfills all the business goals, and then it would basically recommend those settings to control room operator, and then it would then the control room operator would look at those things and determine whether they are safe to implement or not, and then it would ask the controller to implement it. So there's now this added layer of intelligence, which lets you make more meaningful decisions by having a good view of your entire line, which you may or may not be able to do without just through the experience. So this is something, this is what moving towards autonomy looks like. And this is not just an example, it is something that we have actually worked on and have implemented. And after the implementation, we compared the performance before the implementation and after the implementation. And After implementation, the operation was consuming on an average 19% less power, and it improved the life of the physical asset by 44%. So again, if I bring up the same levels of autonomy, what we compared in this case, the industrial case, was this, where you had a controller along with a control room operator, which was operating before, and then you had this added layer of intelligence in level 3, and we saw the difference. However, it is also important to notice here that going all the way to the autonomous operations is not the best option all the time. So basically, the level of automation that you would want to have in your manufacturing facility, it should be driven by what are your business needs and your business values. For example, if your facility is completely manual, probably having some sort of an analysis with a control, which is level 2, it could add an enormous value in your operation. While moving from level 2 to level 3, it may not have that much of an impact. So basically, based on your needs, I think the level of autonomy that you would want to have should be decided. So this is what I have for today. I'd be happy to answer some questions if you have any.
Thank you both for such interesting and insightful presentations. Yeah, we're going to welcome any questions. Feel free to raise your hand so we can unmute you, or pop them in the question and answer box below. Awesome. Yeah, here. All right. Oh, here we go. Keith, welcome to the chat.
Hey, good afternoon. Bobby, thank you very much for an interesting presentation. As I mentioned before, I think that sales should be the driving force for manufacturing, because there's no money in manufacturing if there's no sales to go with it, right?
I said amen.
NIRAV, my question is, you're refraining from going to complete autonomy. Is it because the whole system isn't completely understood, or is it, or are there some other reasons that you're refraining from complete autonomy in your of the pipeline?
So in the case of in the case of, I'm not refraining from autonomy, but usually what happens is the industrial systems, they are very safety sensitive, and usually it is, there are small steps. Once you are at a certain level of autonomy, then after that, small steps. So as I said, in this case, we had a level of autonomy, and then we had controller in control room operator in between, basically to assess the recommendations that was given by our system, right? However, that middle part, it can be removed once it is safely do so. The part where I said that those things should be driven by business goal is that usually moving from level 3 to level 4 requires lots of investments and commitments, which may and the end results may not be that much of a value add. It may be possible, it is different for every case, but that was something that I wanted to highlight. But yeah, there's nothing wrong with complete autonomy, as long as it is safe to do so.
I think you hit the nail on the head with the value added part.
Yeah.
As far as the cost to go that final step.
Yeah,
that's a good point.
Yeah.
Thank you.
Thanks for the question.
I'd be interested in finding out how many people who are on the webinar, have thought about moving forward with some AI in manufacturing, but chose not to because of concerns about, is it too expensive? Is it too complicated? Could anybody address that? Maybe another question would be, are people comfortable, are people becoming more comfortable with AI, given that they see so many applications, being developed and offered in the marketplace today that are AI driven?
If I may, I don't want to take over all the discussions, so I want to be careful that I don't ask too many.
Not to worry,
my
Keith.
limit.
Ask away.
But I think that there's still a little gray area in the transition from autonomy to AI. I think that's not completely understood by most of the manufacturing people, and as you know, people in manufacturing tend to stick with what they know. So it's a big step to go to a smart system, if you will.
Keith, that's a very, very good point. It is a big step, but at the same time, it's gotten much smaller in the last 10 years than people actually think. When I first got involved in AI-focused manufacturing back in the 90s, I mean, it was a very different paradigm. Most of the operating systems that that different companies used were proprietary. It was much harder to integrate systems at that time. The budgets for the integration were often greater than the budgets for the software itself. These days, the expertise available, I mean, for example, with NGen itself, through the AI for Manufacturing Association, we have, I guess, almost a dozen large scale and different size consulting firms that specialize in AI in manufacturing. And these days, the opportunity to make the transition can be developed in such a way that it's not as scary. And in fact, you can actually quantify your improvements as you go forth. What I think is most significant, as in our experience with my OptiStress system for secondary wood processing, is that the amount that we invested on the technology side was nothing compared to the growth and benefits that we were able to get from having a system that used machines to do the thinking rather than relying on people, especially when they have to try to do a visual analysis of something in less than a second.
Just to add to that, actually, I think the part where I think there's also this concern about explainability, because when your autonomous system and it recommends some actions or it takes some actions, what used to happen earlier was that there was no explanation to that. But even for this case that I just presented, all the recommendations that we make, we also explain why we are recommending something. If we are saying that if we are asking operator to switch certain pump on or off, we are also saying why, how much power it is saving, and what are the other implications on line, on pipeline basically. And this is the reason why we are recommending this. So probably that may also bring some more comfort and adaptation of this technologies, hopefully.
Awesome. And I'm just gonna let Joel off and allow him to talk here as well. Oh, now it's not giving me the option to. There we go. Hey, Joel. If you have any questions, feel free to ask them. Oh.
have a question, imagining since Bobby's involved with the processing of biofiber, and the types of fiber coming into a processing operation are either known or unknown quantities. How would the system handle that raw material that may gum up the works, let's say, to where you end up recognizing that there's something about the straw that's coming in that's maybe not adequate or to spec, and it appears that it's taking the equipment into harm's way to where it literally could gum up the works? How does AI manage that? Are those determinations of the raw materials coming in before they enter processing, or are there workstations along the way that guide the material to be, let's say, better prepared before going into higher levels of manufacturing? How do you avoid errors and basically having to shut down the line, I guess?
Well, I think that there's two different issues there, Joel. The first one is that we use an automated quality control system, which again is integrated directly into the overall process in order to evaluate all the bales that come in by doing a preliminary test on the bales themselves to determine what the internal material characteristics are of the fiber. And in that way, we are able to qualify specifically what those characteristics are. And again, using machine learning over time, you would have the benefit of knowing specifically which characteristics are most appropriate for which products, and which characteristics would render the product or render the fiber to be inappropriate for specific products. The other thing, though, is that once the system is tracking the fiber from each bale, it actually can keep a record of which farmer, for example, provided that particular bale. It would keep a record statistically of what percentage of the bales from that particular farmer came in substandard, and what the yield would be off, or the average yield would be off of each particular farmer's feedstock. The system would do this automatically. Because the system is in complete control in our specific facility of all of the monitoring, controlling, synchronizing, and directing, because whatever the fiber is analyzed by the control system to be appropriate for, the system would automatically direct that particular portion of the fiber to a specific production line to be directly made into a finished product. Does that kind of address the question?
Well, it does. I mean, in other words, you are tracking the farmer or supplier on the quality of their stuff coming in. It's analyzed before it hits the line, let's say. But does this end up actually just limit the occurrence of shutting down a line? Are there any safeguards where something might catch a mistake and then you basically save a total maintenance catastrophe? Or, I mean, wouldn't those protocols be in place for, let's call it more traditional non-AI manufacturing?
Well, very good point. And in fact, the system does safeguard itself. One of the elements of AI in manufacturing in a discrete manufacturing environment is that you would monitor all of the pumps, all of the motors, all of the drives, all of the valves. And if the system started to learn of restrictions or certain changes in the static or the regular condition of the production, that would indicate that there is some type of distress in the production line. The system would automatically recognize where it's coming from. Its machine learning would have probably given it some insight on how to handle that problem from previous experiences. But the truth of the matter is, if it became anywhere near a problem that could jam up the machine or create problems, the system would automatically turn itself off, allowing you to do what would be necessary to avoid that type of problem. And for that reason, and others, your productivity gain when you're using AI for M is significantly beyond anything you could achieve in simple automation.
So you still need tech on the floor, but instead of repairing multiple pieces of equipment that may end up being gummed up, there's a great fail safe to where the maintenance that might occur is, I guess, it's headed off at the pass, and it's not as catastrophic a shutdown.
Well, that's part of it. The other thing is that in AI for manufacturing, you get the benefit of automatic predictive and automatic. My God, automated
Predictive analysis. Yeah. Okay.
predictive
Yeah. No,
predictive
I get it.
maintenance. So the
Okay.
maintenance, the maintenance history is stored within the system itself, letting you know approximately what the life expectation is of specific valves or specific motors or pumps. And those would be,
TPM comes in as a report based on what the run of the raw material might be, or just the general operation. So total productive maintenance would automatically be a part of the system's operation.
yes, it would be self-monitoring and self-advising. And in fact, to that extent, the system would be able, because it integrates into all of the systems within the operation, it would be able to automatically arrange to order, it would automatically order the pump that's required, and it would automatically define within the production scheduling, which it also is responsible to produce, exactly when that change of a motor, for example, would take place.
Okay, great. Just thought I'd create hypothesis. Thank you.
Thank you.
Awesome. We'll turn to Mary here, and I'll let you off mute.
Hi, thanks. Are you able to hear me?
Yes.
Okay,
Mary.
great. Thanks. Hi, NIRAV and Bobby. Thanks so much. Those are really great presentations. I'm here maybe with a human factors question. So one of the challenges that I've witnessed in the adoption of more automation in manufacturing and things like AI that would be useful to me personally, though, is the view that this technology is a threat to jobs, and particularly coveted ones, such as in the control room that NIRAV sort of touched on there. So I just wondered if you guys had any thoughts on what we can do to sort of align the value of the humans with the added value of this technology.
Mhm.
NIRAV, would you like to start on that one, please?
Yeah, for sure. Yeah. So the way I think about this is, if you are taking some of the work from operators, they would have more time to think about, I would say, about other things than just worrying about these things. Usually, when we look at the technologies, I often use this example that if you are in a school, you're doing master's or PhD earlier, you used to go to the library to find the relevant research that you are working on. Now, in those days, you would be in your PhDs, you would be able to publish 1 or 2 papers during your PhD. Now you have Google. So with just a simple click, you would find all the things that are relevant to your research that's been going on. Now you're publishing 4 or 5 papers. So I think it usually helps rather than replaces the function or job. That's my view on it. I don't know whether I addressed your question or not.
No, that's a really good answer. Thank you.
Well, I'd like to add to that, Mary, if I may. I think the other thing is that the technology also provides for other jobs to adapt to the realities of an AI-driven environment. For example, when you're looking at maintenance, or you're looking at just monitoring the control systems, because all of these systems are able to be presented using a digital twin, the opportunity is to have people have greater visibility into the actual logic structure and operations of the line, and they would be able to get a much better understanding of how the pieces of that overall system fit together. So they would have a much better time in terms of trying to address a problem or repair a problem, much the same way that the digital twin technologies, which is an inherent part of AI, would allow them to have the type of transparency that would allow for VR or virtual reality to be able to break out what the exact problem is and provide a visual means of exactly what steps need to be taken to repair a problem. Within the control room, I think it also means that, whenever the system does have a concern or a problem that it's facing or anticipating, it will in fact rebound to the control room and have the benefit of being able to interact with a human operator to give it, more specific instruction or clarity, if that's in fact what the system needs.
Yeah, thanks so much. I think that's a really compelling point about sort of how quickly we can go from information, knowledge to insight, right? So a lot of the time,
Perfect.
these guys on the line or rather in the control room have been there for 20 years and they have a pretty good idea of what's going on, but we don't want to take 20 years to really understand the problem. The more people that can help address a problem, hopefully the quicker we can solve that. So I like that very much. Thank you. Yeah.
Thank you.
Awesome. And Ty, will let you off mute here if you have a question as well. Yeah, we can hear you.
All right. Yeah, thank you both, Bobby and NIRAV, for the presentation. That was great. And you as well, Nicole, for keeping it all together. I'm just wondering, so do you find that these AI optimization models work well when applied to other industries like automotive manufacturing or food and bev? Or for now, do you see most of the use cases in process automation, like oil and gas and pulp and paper?
These applications, Ty, are everywhere. I mean, the reality is, for the most part, most people have no idea that the products that they're getting were or were not made in an AI environment. But you get very specific benefits out of an AI produced product, such as more consistent quality control and a better understanding of which batch a particular product came from and made. So if there is a problem, it can go back to the manufacturers with much greater clarity and purpose. So the way that I look at it is that you can use the logic structure of AI in manufacturing, whether it's for discrete manufacturing or whether it's for chemical processing, because the hidden piece that actually makes such a huge difference in this type of application is your system architecture. And a system architecture just basically looks at data in and data out. And it's agnostic. It doesn't really care whether the data in is, from one particular system or another particular system. It's just data. And as far as the data out goes, it doesn't care whether it's communicating to a drill or a saw or to a batch of chemicals that's being processed over a period of time with specific application. So I think that, you know, AI is going to become ubiquitous. I mean, it is already having such a profound impact on, you know, so many different opportunities, which up until now just wouldn't have been possible without this type of depth and and computer power and flexibility that AI in manufacturing provides.
And to the other point that you just mentioned, we are actually right now currently working with someone in food processing as well as in pharma. And where this kind of optimization helps them is usually resource allocation, the switching off the batch when you have a production line. You will always have some downtime in between, right? So how do you minimize that? How do you schedule your product, which would minimize your switchover times, or even failure prediction also helps. For example, since you have this sensors that are laid out throughout your facility, it can monitor and it can also predict that you have at least, say, for example, 1 month or 10 days or 5 days before you have to go and take care of this equipment or basically do a maintenance. So basically, having AI and this automation allows you to look at this thing all at the same time continuously, and I think that is how it adds value in those sectors as well.
And the machine learning component of AI adds this incredible capability, which is continuous improvement. So, you know, the point is that if there is a problem or a failure, the beautiful part is that the system will tell you what happened. And, you know, instead of having to hunt for it and try and figure out what happened, you'll get the benefit of the system telling you immediately. And again, once that expertise has been transferred from the system to the operator is that much more competent and capable, and you're going to end up with much fewer problems and a much improved bottom line.
Awesome. Thanks, guys.
Thank you.
Thank you.
Awesome. Just in the essence of time, we'll wrap it up here. Thank you so much, everyone, for joining and all of these awesome questions as well. Thank you to our hosts today. It was a great discussion. I have popped just the AI for manufacturing website in the chat box if anybody is interested in learning more. We are, you know, a new non-for-profit in the industry and work very closely with NGen. Exciting things to come. Yes, Robert.
I would just like to add for the people who have joined that, you know, I'm not an engineer by background. I'm a business person. And, you know, my understanding of AI came from the actual applications that I've done. And I would be very happy to speak to anybody who might be interested in, you know, again, learning more, again, from a non-technical point of view, but more from an application perspective as to how they might be able to benefit from AI in manufacturing in their particular business. So I just make that as an open invitation. And thank you again, Nicole, for putting all of this together. Really greatly appreciated.
Thank you. Yeah, awesome.
Thank you,
Alrighty.
Robert.
And thank you, NIRAV, of course.
Perfect. End it here then.
Goodbye, everybody.